Okay, in these slides we want to discuss circuit connection in series between two capacitors in series. So you have C1, these are the two plates of capacitor 1, these are the two plates of capacitor 2. And initially, before the switch is closed, everything is neutral. The wire itself is neutral, it has equal positive and negative charges, the plates are neutral, it has equal and positive charges. What happens when you close the switch and there's a battery connected in the circuit? When you close the switch, an electric field is created inside the wires, and now how will the charges on the plates and in the wires be affected by this electric field? So negative charges on this plate will go opposite the electric field and go into the wire, and they will move in the wire, and an equal amount of negative charge on this side will go onto this plate. It will go opposite, the negative charge here will go opposite the electric field also, and it will go onto this plate. So in the end, this plate becomes positive and this plate becomes negative. And exactly the same amount of charge that leaves here will go here. It's not the fact that this charge is the same one that arrived here, but because there cannot be any buildup of charge on this wire, the total amount of charge doesn't change on the wire. So if any negative charge goes in here, another one, the one that exists here, has to go out. So we have a situation after some time that this plate has charge minus Q and it's negatively charged, and this plate has charge plus Q and it's positively charged. And this negative charge and this positive charge will make an electric field. This one will make an electric field this way, this one will make an electric field towards it. And these negative charges will repel negative charges on this plate to leave the plate and be attracted towards this plate closer to the positive charge here. So some negative charge will go off this plate and onto this plate. So this plate, in the end, it will acquire exactly the same amount of charge but opposite sign to this plate, and this plate will acquire a certain amount of charge exactly an opposite in sign to the charge on this plate, and the charge on this plate will have to be the negative of the charge on this plate. So this is what the situation would be when the circuit is completely closed for a long time. When the capacitors are fully charged, this capacitor reaches a charge plus big Q, this one has a charge minus big Q, this one has plus big Q, this one has minus big Q, and the electric field in the wires becomes zero. When the charging process stops, the electric field goes to zero. When the electric field goes to zero, that means the potential everywhere on this part of the circuit is the same. So I put this in one color, red color. The potential on this part is all the same. I put it in green color. And then the potential on this part is all the same. I put it in blue. So the question, let's go back to this issue of the charges on the capacitor plates. Why must these charges, the one here and the one here, be equal and opposite? Because we're assuming that, remember, this plate and this plate are not connected to the circuit at all. In fact, this is empty space here between here, and it's empty space between here. So these two are not connected to the circuit, so they always have to remain neutral. There's no charge that is transferred to these two plates. So that means that any charge that leaves this plate has to go on this plate. We're assuming that there's no buildup of charge on this wire. So if this is the case that we're talking about, where there's no buildup of charge on the wire, then any charge here that leaves this plate goes onto this plate, and the sum of the total charge on both plates has to be neutral always, because initially it was neutral. Why must the charge on these plates be equal and opposite? Well, these plates are assumed to be very close to each other. If you make a simple argument for an ideal capacitor where the two plates are very close to each other and there's no leakage of electric field lines outside the capacitor, then we can, and the electric field is uniform in the region between the two capacitor plates for this parallel plate capacitor, we can make a simple argument. If you apply Gauss's law, make a Gaussian surface, a volume, that this face of the volume lies inside the capacitor plate, and the back face also lies inside the capacitor plate, and then you have the top and the bottom and the front and the back. The angle is 90 degrees between the area vectors and electric field vector, so it gives no flux. and the electric field inside the conductor is 0, so you get 0 flux, and the electric field inside this conductor is 0, you get 0 flux. So when you apply Gauss's law, the left-hand side of Gauss's law is 0. That means the charge inside has to be 0. That means the negative charge that's here has to be exactly the same as the positive charge that's in here. Remember, this surface, it exists inside the capacitor plate, so it's inside the conductor. This face is inside the conductor, and this face is inside the conductor. So the electric field is 0. So in general, we showed that the charge on this plate has to be the negative of this one, and the charge of this plate has to be the negative of this one, and the charge on this plate has to be the negative of this one. So they all have the same magnitude charge, but they're just opposite in signs. Now let's kind of define points so that we can talk about potential differences between different points. Let's call the point A the left side of this capacitor plate, the point B the right side of this capacitor plate, the point C the left side of this capacitor plate, and the point D the one on the right of this plate. And point E to be on the left side of the battery, point F to be on the right side of the battery. Now we're going to define delta V1 to be the potential here minus the potential here. It's the potential difference across this capacitor. And delta V2 is going to be defined to be the potential here minus the potential here. It's the potential difference across this capacitor. And delta V of the battery is defined to be the potential on the plus side of the battery minus the potential on the minus side of the battery. So let's see what delta V1 plus delta V2 is. So this is delta V1, it's VA minus VB, and this is delta V2, it's VC minus VD, and let's add these two things. When you add these things, notice point B and point C, they have exactly the same potential. So if you have here minus VB and you have here plus VC, this will exactly cancel with this because they're equal and opposite. So what we're left with is VA minus VD. Now, if you look on this part of the circuit, point A has exactly the same potential as point E, and point D has exactly the same potential as point F. So I can replace VA by VE and VD by VF. So you get delta V, VE minus VF, which is delta V. So what we've proved here is that delta V1 plus delta V2 is equal to delta V. So for series capacitors, the potential difference across capacitor 1 plus the potential difference across capacitor 2 is equal to the potential difference across the combination. Okay, now for this particular capacitor, capacitor 1, we know the relationship between the charge Q1 and C1 and delta V1, but Q1 is Q because both charges are the same, so I'm just going to call it Q. And the same thing, we know the relationship between charge, capacitance, and potential difference for capacitor 2. Q2 is C2 delta V2, and Q2 is big Q because it's the same charge on this capacitor plate. So the question we have now is, what is the total charge that's delivered by the battery to the combination of capacitors on either side? This battery, how much charge does it deliver on the left side, for instance? The battery delivers an amount of charge big Q. Remember, the charge on this plate and this plate is not charge delivered by the battery. The battery actually cannot deliver charge to these two plates because there's empty space here and there's empty space here. So all what the battery did is it supplied an amount of charge big Q on this left plate. So if I want to replace these two capacitors in series and put instead of them one capacitor that does the same job here means that on the left side the battery supplies an amount of charge big Q and the right side minus big Q. So for this equivalent capacitor, it exists under the same potential difference, so Q is equal to C equivalent delta V. So this is the original circuit, and this is the equivalent circuit, and we've showed before that delta V1 plus delta V2 is equal to delta V. So now, if you look at this equation, I can replace delta V by Q over C equivalent. And in this equation, I can replace delta V2 by Q over C2. And in this equation, I can replace delta V1 by Q over C1. And that's what you get. Q over C1 plus Q over C2 is equal to Q over C equivalent. Now all these Q's are the same, So I can delete the Q's, and you get this final relationship for the equivalent capacitance in terms of C1 and C2. We have 1 over C1 plus 1 over C2 is equal to 1 over C equivalent. And the potential difference across the capacitors is additive, and it's equal to the potential across the combination, which is the potential difference of the battery. So this slide summarizes the characteristics of connections in series, and the very important thing about connection in series is that the charge here is the opposite of the charge here, is opposite of the charge here, and the charge here is opposite of that. So all these charges have the same magnitude, but they just differ in sign.